Hello friends, today we'll be talking about optical aberrations. Aberration means problem basically. Okay, it's an anomaly. In ideal condition, what is happening or what is expected is when rays of light pass through a lens, all the rays should focus at the same focal length, correct? And you get a perfect PSF or a point spread function, right? So as you see here, just one small drop of water, exactly one smaller drop of water at the center, it will create ripples and it is a perfect Gaussian profile. Okay. Now this is an ideal condition, but in real life, you don't have this ideal condition, right? In real life, what is happening? There are a lot of aberrations which are involved. When rays of light pass through the lenses, you encounter this aberrations. And while capturing your image, your question will be why? Why? And why this problem is occurring again and again, right? So this problem everybody faces, and especially the lens manufacturers, they pay a special attention to this, how this can be rectified. Okay, so first we'll quickly see what are the different types of aberrations which we face in our in case of lenses, right? So namely spherical aberration, astigmatism, coma, field of curvature, and distortion, right? So these are some of them, but the common are the first three. The first three are the most common one and which we face on our day-to-day life. Okay, so I think all of you know and very well aware of this footage. So yes, you can see Bhalal Dev is very keenly, for adjusting the lens setting on here and focusing on the object or the person who is coming up. And we all know who that person is. Yes, Dev enough for sure. Now, if you see this image, the edge of the image is blurry. The center of the image is very sharp. Now, this is not a perfect image. When your sample or whatever you are imaging, it should be equally sharp in the center as well as at the edges. But here, if you see, the edges are not very, very sharp. So, why this is happening? Okay, so the first thing is an spherical aberration. So spherical aberration, basically what will happen when the rays of light is passing through the center, it will go straight as you can see here. Then if as and when we move away from the center of the curvature, so or the center of the lens, basically, you see this is meeting at a focal length f1. But again further, if it is moving away, this green rays of light, they are not focusing at f1, they are focusing at f2, that is in a different focal plane. And if we again go further to the periphery side of the lens, you see the focal length gradually has decreased further. Correct. So this decreasing further is causing what? You have different focal length at different point. And as you can see here, the point spread function is also changing. So you see an outer bigger ring and a small inside ring. Okay, now this rays of light will contribute more and the center one, the rays of light will be contribute less. But this is an anomaly, this should not happen. And how can we rectify this? We can rectify it using aspherical lens, basically. Okay, so aspherical lens, they are of this type, as you can see here. To achieve this, what is this? The spherical surface must be abundant and the lens ground with aplanatic surface, that is the peripheral curvature is less than the central curvature. So simple language, center mein the curvature will be more. Okay, so at the center the curvature will be more and at the edges, जो edges होंगे वहाँ curvature will be less. So you see here this curvature at the center is more and the curvature at the periphery is less. इससे क्या होगा? Simple thing, the rays of light now all it is the design in such a way that whatever from where the rays of light is coming, center se bhi aa raha hai, edges se bhi aa raha hai, they will all focus at the same place and then your spherical aberration is corrected, right? So this is the correction method you use for your spherical aberration. And so you see here if you have a white light and then this is the same white light when it passes through lens, what is happening based on the wavelength? What will happen? According to the wavelength, the dispersion of light varies. So blue will be having the maximum dispersion, red will have the minimum dispersion, and based on that, again there will be different aberrations. Correct. So this is what you say, you see at different angle, you see at the focus of the green light at D, and you see the focus at the blue light at this position. Okay. Now similarly, what we find is, if you see from the other side also, this particular difference, right, is called as residual chromatic aberration. Residual chromatic aberration is because of the color. So aberration because of color has become the residual chromatic aberration. Okay, and as you see here, the the rays of light from different, they are diverted, the angle of diversion is different, and by placing one more lens here, this particular lens here. So in the first case, there was only one lens, this particular lens, and you see the angle of curvature was different. But by placing one more lens, this one, if you can see, what has happened, it is, the angle is here, but again it is rectified, and all are focusing on the same place. So your chromatic aberration is also corrected here. Okay, chromatic is color aberration. Color is associated with different wavelengths, blue, green, red, VIBGYOR, as we know. From blue to your red, the dispersion or the angle of deviation is varies. That is why for different wavelengths, we see they are meeting at different focal length. That can be easily removed if we place another lens like this, and then all the rays or all the wavelength of light will focus at a same place, and you will get a perfectly same focal length for all. Okay. Now the other one is astigmatism. Astigmatism is basically, if you can see here, this is a normal haze night time while you're driving, you see something like this, right? But if it is astigmatism, you see something like this, streaks of light. Correct. This is a problem. A problem means normally your one line, that is horizontal, vertical and horizontal, all both the lines, okay, they cannot be focused at the same time. So if you have a plus like this, either you focus this one, this is out of focus, or you focus this one, this becomes out of focus. Correct. So if you have a cross like this, either of this will get focused and the other one will not get focused, and that is what the problem with astigmatism. How you can find out astigmatism is, if you see here, this is your object plane, and these are the different planes, like if I said the one tangential and one sagittal plane. Correct. So one tangential and one sagittal plane, and if you see, the red one is focusing at the sagittal focus, whereas the blue one is focusing somewhere different at the tangential focus. तो अब इससे क्या होगा, आप या तो focus blue वाले को करोगे या तो focus red वाले को करोगे. You cannot focus both at the same time or the same place at the same focal length. नहीं possible है, right? So how do you correct it? The correction is by means of a cylindrical lens like this. So this cylindrical lens, what it will do, it will take care of the tangential as well as sagittal plane. And then as you can see here, both will focus at the same place. And as a result, what will happen here, you can see this, basically this type of lens is a portion of the cylindrical lens has been cut. So basically a cylinder glass which has been cut on the edges, and this is used to rectify it. Okay. And the last one is your coma aberrations. Okay, so coma aberrations, basically what is happening, it is like a coma. We all know what a coma is. In case of a coma, you see here, this is a lens and the focus is like a coma. So you have one, instead of one center frame where everything is focusing, you see like a comet sort of thing. So at the center, and then there's a fanning out effect. Why this is happening? You see, this is particular lens. Now from zone 1 to zone 3. Okay, so zone 1 to zone 3 and zone 4. You see, first one at the edges, they are focusing in this plane, and gradually this particular spot, light spot is becoming bigger and it is moving away. So it is becoming like a fan shape or a comet shape. Okay. Now This is something is because of the like the cylindrical lens, it reflects light only in the plane perpendicular to the axis of the cylinder. The axis of the cylinder, it defines the non-refractive plane, correct? Now this here, the cylindrical lens can be plus or minus. As you can see, we have cylindrical lens these days for your eyes also. So here, what is the coma aberration? Is basically an inherent property. Uh, Primarily, it was developed or it was identified in telescopes where a parabolic mirrors were used. Unlike a spherical mirror, a bundle of parallel rays parallel to the optical axis, okay, will be perfectly focused to a point. Now, the mirror is free of the spherical aberration. We have to consider that. Now, no matter where they, strike the mirror. However, this is only true if the rays are parallel to the axis of the parabola. Now, when the incoming rays strike the mirror at an angle, individual rays are not reflected at the same point. So when it is coming same, they are focusing, but when it is at an angle, they are not focused at the same point. When looking at a point, this is not the perfectly aligned with the optical axis. So some of the incoming light from the point will strike the mirror at an angle. And this causes an image that is not in the center of the field to appear as like a wedge shaped. Okay. And further off axis or the greater this angle, okay, the worse this effect increases. So this causes stars to appear to have a cometary coma. So as I was saying, like a comet. So it was like in telescope also, we had this problem. And hence from there, the name has been taken as a coma. Now, there are there are different schemes to reduce coma without introducing spherical aberrations, including uh, optical systems. Look, so what it is done is like the correction lenses, the coma correctors are also called as Newtonian reflectors, have been designed in such a way to reduce the coma by a factor of f by 6 divided by, so the focal length is divided by 6. Okay, so this work by means of a dual lens system of a plano-convex and a plano-concave lens fitted into an eyepiece adapter. Okay, so coma of a single lens or a system of combination of lenses can be minimized by choosing the curvature of the lens surface to the match the application. Correct? So lenses in which both spherical aberration and coma are minimized at a single wavelength are called best form or aplanatic lenses. Now, aplanatic lenses are where this is both the corrections. So for more versatile correction of coma, one can use a combination of two lenses, both of which are corrected for zero coma at infinite object distance. Okay. Now, the appropriate separation of these two lenses can correct for coma at various object distances also. In case of like coma can also be corrected by appropriately putting a stop, but the placement and the size of the optimum stop depends again of the aberration and the intensity of the aberration here. Okay, so I think today I tried to cover basics of the types of aberrations and how we can correct these aberrations in our lens so that you get an image which is corrected and that has that is aberration free rather.